Back to buffers. I'd now like to look at a buffer actually buffering. This presentation, like all of these, is going to assume a certain amount of prior knowledge. And so, again, I ask that you recall what we know about Ka and Kb reactions, right? That's any acid or base with water. And then what's termed K neutralization reactions. This is any acid or base where neither one of them is water. And then previously we've looked at what to do when you have multiple acid-base mixtures. This is especially important for buffers because inherently buffers are mixtures of acids and bases. And if I have a buffer, I remind you that Henderson-Hasselbalch gives me a relatively short way to solve for the pH, which I'm going to use here. And so a buffer by definition is a solution that resists changes in pH. We've seen two ways you can make buffers, right? No matter how you get to the buffer, once you have a buffer, it should resist changes in pH, right? It's worth asking why the pH would be changing. I mean, if I just have a solution sitting there on the counter, I don't expect that anything's particularly changing. And so inherently, a buffer really serves the purpose of mitigating against the addition of some other acid or base, right? That's why the pH wants to change. I've thrown some other species in there that has acid or base properties. As a result, if I want to see a buffer actually buffering, I'm always looking at a mixture of multiple acids and bases. And so here's an example of a buffer trying to buffer. I have a solution made by mixing 500 milliliters of 3 molar NH3 ammonia and 500 milliliters of 3 molar ammonium chloride. And I ask the usual question, what is the pH, this time of the solution after I've added 10 milliliters of 1 molar HCl? Now, I already gave away the answer. This is a buffer problem. It may not be immediately obvious it's a buffer problem because what I really have up front is a whole bunch of things I threw together. And quite frankly, standard student psychology says, hey, he threw a whole bunch of things together, make them all react, right? No way, no how, not ever. What I really have here is a whole bunch of acids and bases, right? And the key to acids and bases is that they always react single acid, single base, single proton. I don't try to make them do more than that ever. Right? And so everything in this problem has acid or base properties. For two of them, it may be relatively obvious if I ask the question, ammonia, what is it? We've seen it before, right? We know it's a base. HCl, what is it? It's a strong acid, but it's an acid. We have seen it before. And ammonium chloride, what is it? Well, it's not an acid, and it's not a base. And it falls into my third category. It's a salt. And so the first thing I do with any salt, when it's dissolved in water, and this is dissolved, the molarity tells me so, is I dissociate it. And so I don't really have ammonium chloride. I have ammonium cations and chloride anions. Right. If I do that, it may become more obvious that this is a buffer because I have ammonium and ammonia, and that is a conjugate acid-base pair. Right? And that is what I'm looking for in a buffer, is I have some of the acid and some of the base for the conjugate acid-base pair. And so it is a buffer problem, right? And I'm going to Henderson-Hasselbalch it, right? But the buffer is really only formed by the ammonia and the ammonium. What about the HCl? Well, again, I go back to what I said a minute ago. What I really have here is multiple acids and bases, right? HCl is just another acid in the mixture, and it's going to do the one and only thing that acids ever do, which is donate a proton to some base. And so whenever I have more than one acid or more than one base, I separate them, right? All of the acids in one column, all of the bases in the other column, and each one of the acids should react with each one of the bases because they don't know. They don't choose, they bump into whatever they bump into. And so in this particular case, I actually have 3 acids and 3 bases. Right? The HCl is an acid, the ammonium's an acid, the conjugate acid of ammonia, and good old water, both an acid and a base. Right? And on the base side, the ammonia is a base, and the chloride that dissociated from the ammonium chloride is in fact itself a base. So technically, I have 3 acids and 3 bases, and if I really wanted to go hardcore on this and crunch all the numbers, there's 9 reactions I could have, and technically they all happen, and they all have to reach equilibrium. But if I'm at least a little clever here, I can actually throw some of them out. Right? First of all, chloride is the conjugate base of HCl, and HCl is a strong acid. Right? So I can calculate the Kb of chloride from the Ka of HCl, and typically for a strong acid, the Kas are thought of as being nearly infinite. And so if you do the math using the nearly infinite, right, as you might recall, the Ka of an acid times the Kb of its conjugate always equals Kw. And so the Kb of chloride should be the Kw over Ka. And if Ka is nearly infinite, right, the Kb of chloride is essentially 0. Right? What that means is all 3 chloride reactions aren't worth thinking about, right? Because no matter what I add to chloride, right, so chloride as the base, plug in really any acid you want, the K neutralization for that reaction, as always, is the Ka of the acid times the Kb of the base divided by Kw. But the Kb of chloride being essentially 0 means no matter what I use as the acid, the K neutralization is going to be 0. And so chloride is a classic spectator, right? That is one of several reasons why chloride is a spectator, because it's really not good at doing much of anything. We'll see it again in a different spectator role later in the semester, right? But so it's not really worth considering the chloride reactions. And so I'm down to 3 acids and 2 bases, which is only 6 reactions. But since ammonium and ammonia are conjugates of each other, technically speaking, I'm always sort of solving for both of them simultaneously, because every acid-base reaction for one of them has the other species in it, right? Because, of course, the only thing that ever happens in an acid-base reaction is a proton goes from the acid to the base. So if I start with ammonium, I'm going to end up with ammonia. If I start with ammonia, I'm going to have ammonium as one of the products. And so I'm always really solving for both of them. And so I can sort of ignore ammonium as a separate species, and I'm down to 2 acids and 2 bases, which gives me 4 possible reactions. It's the same 4 possible reactions we saw in the previous video. Right? I have ammonia as one of my bases reacting with either of the 2 acids, HCl in a K neutralization reaction, or water in a Kb reaction. And I also have water as my other base reacting with the 2 acids in the mixture, the HCl and the water again, right? 3 of these I know or could look up, right? The Kb of ammonia is in the table in the back of the book. Or, of course, pick your favorite internet reference. Kw, of course, is also a known quantity and can be looked up at room temp. It's 1 times 10 to the minus 14. And again, since HCl is a strong acid, technically speaking, its Ka is usually thought of as being infinite, but because I have 2 infinite numbers here, I want to rank them, right? I tend to just call the Ka of my strong acids frickin' big, because when I calculate, and I have to calculate the K neutralization in the top reaction, it's the Ka of the acid times the Kb of the base over Kw, right? If I plug in the numbers, I get essentially 2 billion times frickin' big. Or as I like to term it, super frickin' big. right? And so in terms of size, right, my ammonia HCl reaction has the biggest K, right, followed by the HCl Ka reaction. Both of those have near infinite Ks. And so really both of those are not actual equilibria. They're limiting reactant problems. The other two, right, are in fact equilibria and will require me to solve the equilibrium problem as I normally do. Right? But technically speaking, all four of these reactions have to get to equilibrium, and computationally, I bring each of them to equilibrium one at a time separately from biggest K to smallest K. So I'm going to start with the top reaction, right? Go to the third reaction here, the HCl with water, right? And then the third and fourth Ks in order. I'm going to make an ice chart because it's an equilibrium problem. I always make an ice chart. In this particular case, I'm going to do the ice chart in moles because it's easier. I don't have to worry about dilutions. If you wanted to calculate the molarities, you could. But it's just easier, especially because I'm going to use Henderson-Hasselbalch if I do this in moles. And so I added 10 milliliters or 0.01 liters of an HCl solution that was 1 molar. So I added 0.01 moles of HCl. And similarly, I had 0.5 liters, 500 milliliters of a 3 molar ammonia solution, right? And 0.5 liters of a 3 molar ammonium solution. So that's 1.5 moles of each of those. Technically, added on the fly, right? There was chloride present from the ammonium chloride. But again, the chloride's really just a spectator. It doesn't appear in any of the other reactions, so I almost don't even need to track it. Right? Because it's a super frickin' big K, it's a limiting reactant problem. And so the signature of that is that something goes to zero, whatever there is stoichiometrically less of, in this case, the HCl. So 0.01 moles minus X equals 0 means X is 0.01. And so it's 0.01 everywhere. Right? And so you can see what the HCl did in the first reaction is actually change the amount of ammonia and ammonium. It turned some of the ammonia into its conjugate acid, ammonium. Right? At that point, my first reaction's done. I would go to my second reaction, right? But the second reaction relies on having HCl. I'm out, right? And so I skip right over that reaction and go to the next biggest reaction I can do, which is the ammonia reaction with water. Right? This is my buffer reaction. I have an initial amount of both conjugate species, and if I recognize that it's a buffer, I can just straight up Henderson-Hasselbalch it. If not, I can always go through, write the K equation, and solve the K equation. That's all Henderson-Hasselbalch is really doing for me. Right? And if I do that, I use the POH version of Henderson-Hasselbalch because it's a base. I get a POH of 4.75, which gives me a pH of 9.25. Now, by itself, that number tells me nothing, right? What I really want to do is compare it to the number I would have gotten, right, had I not added the HCl. I point out, I'm not a big fan necessarily of these, but a lot of internet sources use them, right? Sometimes instead of doing two separate ice charts like we just did, they stack them into a double ice chart, which one of my prior classes nicknamed an icicle chart. It's a little confusing sometimes because the top half of the icicle chart is really a different reaction than the one at the top of my ice chart, right? Ultimately, I'm trying to do the ammonia-ammonium reaction, but this super frickin' big neutralization reaction changes the initial conditions for the ammonia reaction. And so it is sometimes shorter, if this doesn't confuse you, to do it as a double ice chart. If not, do it as a completely separate pair of ice charts, right? And so, again, I get my 9.25 no matter which way I do it, double ice chart or two ice charts. that is the buffer after I add the HCl. The problem didn't ask me to calculate it, but just for comparison purposes, if I actually calculated the pH of the buffer before I added the HCl, when I had 1.5 moles of each, the pH was 9.26. So you can see that I added a strong acid, HCl. It made the solution slightly more acidic. The pH went down, but it didn't go down very much. Right? This is what I would expect a buffer to do. It should be minimizing the changes in pH. Right? For comparison purposes also, right, if I added the same amount of HCl to a solution that had 1.5 moles of ammonia, but no ammonium, right, this is not a buffer initially, right, and I do see a bigger pH change. Right? I won't spend a lot of time on the details. They're here if you want to look at them. But if I look at the ammonia by itself, right, I get a pH of 11.72, right? All equilibrium problems have a balanced equation, an ice chart, and a K equation, and there they are, right? And if I then added that little bit of HCl, here I did it as a double ice chart using molarity because my K equation demands it, right? And what I see is adding a little bit of HCl, again, the top part of the ice chart is actually the HCl plus ammonia going to NH4 plus Cl minus, right? My pH, same amount of acid, right, as prior, changed the pH now from 11.72 to 11.43. That is a much bigger change than when I had the buffer solution. Same amount of acid, same number of moles of ammonia, right? Much bigger change when the ammonium isn't present. And that is a buffer buffering. Right. I'll point out you could do the same but opposite if you actually added a base like sodium hydroxide instead of an acid, right? The essential structure of this problem is exactly the same. The difference is, right, I now have an extraneous base instead of an extraneous acid. But of course, the only thing an acid and a base ever do is transfer a single proton from the acid to the base. So it's not going to change a lot. Right, again, in this case, I have essentially two salts. My ammonium chloride, which I immediately dissociate into ammonium and chloride. And sodium hydroxide, while being a strong base, is also a salt. So I also immediately dissociate it into sodium and hydroxide. Right? And it's really the hydroxide now that reacts with the ammonium in, again, a neutralization reaction that is super freaking big. Right? The Ka of ammonium times the Kb of hydroxide, which is approximately infinite, freaking big, divided by Kw will give me a super freaking big K. So again, it really just does the same but opposite. It turns now the acidic member of the conjugate acid-base pair into more of the basic part. So I now have less ammonium and more ammonia. Right. And again, this neutralization reaction is really the top half of that ice chart. And so now, instead of going down by 0.01, right, the pH went up by 0.01. So again, you see the same basic issue. I add a base to a buffer, it becomes more basic, right? It just doesn't change very much. Right. Inherent in what we just did is that buffers are limited, right? Because if I keep adding acid or I keep adding base, I keep converting one of the conjugate species to the other, right? Again, I could do this as a double ice chart. I will do it as two separate ice charts because I think it's less confusing that way, right? The basic structure, whether it's an acid or a base, just kind of changes the reaction slightly, but the same basic thing will happen. If I'm adding this external acid, right, it's always a super freaking big K. It always goes first, right? It's always a limiting reactant problem. And what happens is I decrease the amount of base and increase the amount of acid, which is then the starting point for what's essentially my buffer reaction, right? And so you can see what happens if I add a little bit of acid, right? It all goes away, right? I now have less ammonia, a little more ammonium. The pOH from Henderson-Hasselbalch is 4.8. The pH is then 14 minus the pOH, right, or 9.2, right? It's now dropping. Remember, it was 9.25 before. We're down to 9.2. If I add a little more, now I add half a mole of HCl. Again, the ammonia has gone down by a half. The ammonium has gone up by a half. The pOH is 5.04. That gives me a pH of 8.96. So it's become even more acidic, right? And of course, at some point, if I keep adding acid, I get to the point where I've added as much acid as I had ammonia there in the first place. I'm out of ammonia, right? I have completely destroyed my buffer, right? At this point, what I have is a solution of ammonium, which is just a weak acid. Without a conjugate present, no buffer, right? Try Henderson-Hasselbalching that with a 0 either in the numerator or the denominator. Either way, your calculator will scream at you, right? At this point, my buffer is no longer a buffer. It's just an acidic solution. So if I start adding more acid still, it's just going to get more and more acidic, and it's going to take really big jumps in pH now because there's nothing buffering it, right? As a result of this, it is usually important to not just specify what the pH of the buffer is, right, but to also specify what the limit on the buffer is, right? Because at some point, my buffer's gone, right, and maybe I'm just acid, right? If I had more HCl than I had ammonia, I made a whole bunch of ammonium, but now the limiting reactant is actually ammonia, and this is just an HCl solution. Right. And so all buffers have limits. This limit is referred to as buffer capacity, and that is the topic of our next video.